Okay, students. So today in this lecture we'll discuss about Coulomb's law, right? So in the previous lecture we had discussed about the charging method of the bodies, right? Mainly we had discussed about charging by friction, conduction, and induction, right? Okay, so now today we'll discuss about Coulomb's law. See, first of all, Coulomb's law. Coulomb is the name of a scientist. And Coulomb's law is basically the law explaining the force between two charges. Right? That means, suppose there is a charge Q1, let us say another charge Q2 is placed at a separation R. Since both the charges are positive, they will repel each other with a force that is given by Coulomb's law. Okay, so Coulomb's law is the law that gives the force between two stationary point charges. Coulomb's law is the law which gives the force between two stationary point charges. Now, stationary means which are at rest. Stationary means charges which are at rest. Okay, and another is stationary point charges. Point charge means, what do you mean by point charge? Hmm? If the dimension of the charge is very less than the distance between two charges. This type of charges are known as point charge. That means if the diameter of the charge is quite less than the distance between two charges. Suppose, say in this case, let the diameter of the charge be d. Let this be the diameter of the charge, d. Right? If d is less than r, then the charge is termed as point charge. Okay, that means if the diameter of the charge is quite less than the distance between two charges. Fine. So Coulomb's law is the law explaining the force between two stationary point charges. Okay, stationary means charges which are at rest. Apart from this, there are certain other properties of this law. It means that it is a centralized force. It is a centralized force means force between two charges will always act along the line joining the charges, right? That means if these are the two charges, Q1, Q2, this is the line joining the charges. So the force between Q1 and Q2 will always act along the line joining the charges. That means either this direction or this direction, this way. Clear? Clear? So force between two charges will act along the line joining the charges. Fine. So that is centralized force. Coulomb's law is not valid for a distance less than 10 raised to minus 15 meter. Okay, that means for a distance less than 1 femtometer, we cannot apply Coulomb's law. Okay, so now, got it? So now the force between two charges, two stationary point charges, according to Coulomb's law, this force is proportional to product of charge, directly proportional to product of charge, and inversely proportional to square of the distance between them. The same thing you must have studied in the law of gravitation, right? That is F was proportional to m1, m2, and F was inversely proportional to r square. Exactly in the same way, the force between two charges is directly proportional to product of charge and inversely proportional to square of the distance between them. See now. So basically, F will be equals to K Q1 Q2 divided by R square, where K is known as Coulomb's constant. Coulomb's constant, whose value is 9 into 10 raised to 9. 9 into 10 raised to 9. Newton meter square by Coulomb square. Is the value of Coulomb's constant. Clear? Clear? Okay. Now, K is actually obtained with the help of this formula 1 upon 4 pi epsilon naught. 1 upon 4 pi epsilon naught. Right? Where epsilon naught, this represents epsilon. Epsilon. Epsilon means electrical permittivity. Electrical permittivity of air. Electrical permittivity of air, or you can say free space. Free space. Clear? Done. So epsilon naught is electrical permittivity of air, free space, or even vacuum, whatever. Actually, in a way, air and vacuum are two different things, but it's okay. We'll take theoretically same. So, see, of course, this will be a new word for you. What is epsilon naught? What is electrical permittivity? Right? And what is the value? What does epsilon naught represent? See, again, I'm repeating the law. Force between two stationary point charges is directly proportional to product of charge, and it is inversely proportional to square of the distance between them. That is, F is directly proportional to Q1, Q2, and F is inversely proportional to R square. Okay, so removing this proportionality constant, we need to multiply a constant, that is say K, which is Coulomb's constant. Okay, now, and the value of Coulomb's constant in SI unit is 9 into 10 raised to 9 Newton meter square by Coulomb square, which is obtained from this formula 1 by 4 pi epsilon. This is the formula. Clear? 1 by 4 pi epsilon naught. Epsilon naught is electrical permittivity of say air, free space, or vacuum. Right? Now, what is the meaning of this epsilon naught? What does epsilon naught represents, and what is the value of epsilon naught? Okay, see. Epsilon naught is termed as electrical permittivity, and the value of epsilon naught is for air or free space, it is 8.854 into 10 raised to minus 12. This is the value. Okay, so epsilon naught is having the value 8.854 into 10 raised to minus 12. See, we had placed two charges in air, clear? Q1, Q2. They are at a distance of r, right? Q1 will repel, Q2 will repel Q1, and similarly Q1 will also repel Q2 because both are having same polarity. That means two positive or two negative charges will repel. One positive, one negative will always attract. Okay, so now, say students, how a charge Q1 and a charge Q2, which are not in contact with each other, right? There is no physical contact between Q1 and Q2. They are separated by distance r, but yet they are repelling each other. They repel each other with a force given by Coulomb's law, that is K equal to R square, right? So basically, in your 11th class, we had studied about two types of forces, right? One is contact force, and another is field force. One is contact force and another is field force. Contact force, that means by making a physical contact with another body, you are applying the force. But what is field force? So, field force is a force which is produced by some kind of field. That means we had studied in the chapter of gravitation that if this is Earth, let us say mass is m. So every object is attracted towards Earth because Earth is producing its own gravitational field. Clear? Right? Magnet will produce magnetic field. Suppose there is a magnet, okay? It's a magnet. It's north pole, south pole. You are placing any iron rod close to the magnet, then it is found that the rod gets attracted towards the magnet because of the magnetic field. Because of the magnetic field. Clear? So, this is not contact force. This is not the contact force. They are attracting because of the field produced by the mass or by the magnet. Clear? In the same way, both the charges placed in air will exert force on each other because they will produce some field, right? They will produce some field which is known as electric field. That is what we are going to learn in our next. We are going to discuss in the next session, in the next, or maybe next to next video, right? So the cause of repulsion or attraction is the electric field produced by the charge. Clear? Q1 will produce some electric field, Q2 will produce some electric field, and because of this electric field, they will experience a force of attraction or repulsion. Okay. So epsilon naught is, it is the property of the medium to, you can say in a way, absorb the electric field produced by the charge. Okay, so epsilon naught represents the property of the medium to absorb the electric field produced by the charges. Say, I'll make this point very clear to you by giving an example. Suppose this where the charge is. Q1, let us say Q1 is producing 100 electric fields. Okay, 100 electric fields. This 100 electric fields will repel this charge Q2. Okay, so Q2 will experience a force F equals to K Q2 Q1 by R square because of the 100 electric field which is produced by Q1. Clear? Q1 is producing 100 electric field lines, right, which will repel Q2. But let us say the medium is a medium. This medium, okay, this medium is absorbing 40 electric field lines. 40. So from 100, 40 electric field lines are being absorbed by the medium. So Q2 will experience a force because of 60 electric field lines, because out of 100, 40 are being absorbed by the medium. So it will experience a force because of this 60 electric field line. Clear? So this 40 is the electric field line absorbed by the medium. That is known as permittivity. That is known as permittivity of the medium. Clear? So permittivity means the number of field lines a medium will absorb. That is known as permittivity. So more the permittivity, less will be the force, obviously, because the more number of field lines the medium will absorb, the less will reach to another charge Q2, and the less repulsion Q2 will have to face, or any other charge has to face. Okay, clear students? If suppose I'm replacing it by any another medium, if I'm replacing it by, say, any medium, say this is another medium. Okay, so now let us say it is absorbing 70 field lines. Okay, so now Q2 will experience a force because of 30. See, so permittivity is more, 70. So force will be only because of this 30 electric field lines. Clear? So more the permittivity, less the force. Clear students? 30 is not known as permittivity. Don't get confused. 70 is the permittivity because 70 field lines are being absorbed by the medium. So finally, permittivity represents the number of field lines absorbed by the medium. Clear? Okay. So force between two charges is equals to K, instead of K, I'll write it as 1 by 4 pi epsilon naught Q1 Q2 by R square. This is finally the force acting between two stationary point charges. And epsilon naught will have the value 8.854 into 10 raised to minus 2. Clear, students? This is the value of epsilon naught. Okay. Now, on substituting 1 by 4 by epsilon naught, 1 upon 4 into 3.14 into 8.854 into 10 raised to minus 12, you will get the value 9 into 10 raised to. Done? Done, students? Okay? Fine. Now, suppose if both the charges clear, unit will be Coulomb square upon Newton meters. On placing this 1 by 4 pi epsilon naught, you will get the value 9 into 10 raised to 9 is equals to. Okay. Now, what if I am placing two charges in any medium? If I am taking, let us say I am taking both this charge Q1, Q2 in a medium. It's a medium. Now it is not air. Take any medium, suppose glass. You can take any other medium. So now the force between two charges when placed in a medium will be equals to 1 by 4 pi epsilon Q1, Q2 by R square. Say students, make it very clear. Epsilon naught is the permittivity of free space, air or vacuum. When two charges are in air or vacuum. Epsilon is the permittivity of any medium. So when two charges are taken into any another medium apart from air or vacuum, then the permittivity will be represented by epsilon. Clear? Let us compare the force between two charges when placed in vacuum and when placed in a medium. So let us divide this. Fa by Fm will be equals to, taking this ratio, Q1 Q2 R square, Q1 Q2 R square, 4 pi gets cancelled. So it will be epsilon by epsilon. So Fa by Fm is equals to permittivity of medium upon permittivity of vacuum. That is known as relative permittivity, or it is also known as dielectric constant. Dielectric K is known as this is known as dielectric constant, okay? And that was Coulomb's constant, which is 9 into 10 raised to 9. Both are different quantities. This is known as dielectric constant. Dielectric means insulator. Dielectric means insulator. Okay. Therefore, we can say that force in medium is equals to force between two charges in vacuum divided by. This is important formula. That means whenever you are taking two charges from air, from vacuum to any medium, the force will decrease by factor K. See, what does this equation represents? Force between two charges in medium is equals to force between two charges in vacuum divided by. Clear? Where K is known as dielectric constant. K is known as dielectric constant. Dielectric means insulator. Dielectric means insulator. The value of K is different for different medium. Okay, that means K is infinite for metal. For vacuum, K is 1. Value of K is greater than 1 for insulator. Done, students? So K represents your dielectric constant. Okay. So this was your Coulomb's law, which is for two stationary point charges. Okay. Clear? So now in the next video, students will discuss about few questions based on Coulomb's law, right? And then we'll go for Coulomb's law in vector form. Okay. See, Coulomb's law in vector form is very easy, and again an important question. Coulomb's law. Okay, first we'll complete this, then in the next lecture we'll solve the questions based on Coulomb's. Since students force is a vector quantity. So it will have some direction. See, F is equals to K Q1 Q2 by R square. This is the magnitude of the force acting between two stationary point charges. What about the direction? What about the direction? Because force is a vector quantity, it will have some direction. Okay, so Coulomb's law in vector form basically gives us about the direction of the force, magnitude as well as direction of the force. Done? So it is very easy. Let us place two charges Q1 and Q2. Okay. So your x axis, y axis, a charge Q1 is placed. Let R1 be the position vector. Another charge Q2. Let R2 be the position vector. Okay. Now force on charge 1 because of 2. So force on 1 because of 2, this way. 2 will repel 1 because both are having same polarity. So this will be represented as force on 1 because of 2. Similarly, 2 will experience a force in this direction because 1 will repel 2. Clear? So these are the directions of force acting on charge Q1 and Q2. Right? Suppose we want to find F12. You can take any relation. That means you can take F21 or you can take F12. Doesn't matter. But one thing is sure, while discussing about Coulomb's law in vector form, we'll specify the direction of force and we'll also specify the direction of position vector. See, F12. Force on 1 because of 2 is equals to K Q1 Q2 by R square. R square, see students, this thing is important. You don't have to buy at the following thing. See, R square, okay fine. Force on 1 because of 2. So 1 is experiencing a force in this direction. So the distance between them is say x. Clear? Arrow is drawn in this direction, this way, because force is along that direction. Clear? So, clear? This x vector represents the direction of force. Unit vector x represents the direction of force. So x is the distance between two charges. So I will place it as x square. Just a second. Okay, sorry. So K Q1 Q2 divided by K Q1 Q2 divided by R square. R square means the distance between two charges. Let us say it as x square into x caret. Now what does this x caret represent? It's a unit vector. It is to represent the direction of this force. It is to represent the direction of this force. Clear? That means x will have the direction which the force will have. Clear? So finally, see, this is your R2. See students, this is your R2. This is x. And this is R. Okay. Clear? This is your. So see, from the law of vector addition, student, R2, this is head of first vector. From that, you have drawn the tail of second vector, and this is the head. So R1 is the resultant of R2 plus X. Clear? See. First vector, head of first vector, and then you are drawing the tail of second vector, and finally these two heads are drawn this way. So this represents R1 is the resultant of R2 and X. Okay, okay students, so here I can write it as R2 plus X equals to R1. This is from the law of vector addition. R2 plus X is equals to R1. So therefore, X will be equals to R1 minus R2. I hope no student will remember this, no student will by heart these things, because if one charge is positive and another is negative, this vector addition will be changed. So better draw vector addition, and from that represent your result. Okay, so R2 plus X is equals to R1, or you can say X is equals to R1 minus R2. Substitute the values in the equation. So finally, F12 is equals to force on 1 because of 2 is equals to K Q1 Q2 upon X square, say R1 minus R2 the whole square into this unit vector. So it will be vector divided by so on. Clear students? So this is your vector law. This is how we will represent addition of two vectors. Now, in the same way, we'll also find F21. But one thing is there, say in F12, I can still write it as K Q1 Q2 upon R1 minus mode of R2, R1 minus R2 in mode, the whole cube into R1 minus. Clear? Similarly, if I want to calculate F21, so F21 means force on 2 because of 1. Force on 2 because of 1. So vector addition will be this one. See. This was R1, this was R2. Here the charge was Q1, charge was Q2. Okay, one more thing. See. See, this will be X. Okay, this will be X. This is your R1, this is your. So now, according to vector addition, this is R1, this is X, this is R2. So now R2 is the resultant of R1 and X. That means R1 plus X is equals to R2. So now X is equals to R2 minus R1. So this will be the change now when you are calculating force on 2 because of 1. Got it? So F21 can be represented as K Q1 Q2 upon R2 minus R1 the whole cube into R2 minus. Done students? Clear? Got it? So F21 and F12, see, still in F21, I can write it as, if I am adding a minus sign over here and I am placing R1 over here and R2, that is same only. I don't need to change the denominator because it is already in magnitude mode. So, but now this is This is equals to F12, right? So finally, F21 is equals to minus F12. So force on 1 because of 2 and force on 2 because of 1 are equal, but they are opposite to each other. Clear? That means Coulomb's law obeys Newton's third law. Okay, fine students. So this was your Coulomb's law in vector form. Clear? So in the next video, we'll discuss about the sums. We'll solve few questions based on Coulomb's law. Okay? Thank you. Thank you.